Good morning, Kevser.
Good morning.
First paper, I think, yours. Okay.
Yes.
Are you ready?
Yes.
Okay. Just a moment. I have time, 1 or 2 minutes to starting. Hello, dear participants. Greetings to you from Bursa. Welcome to the 13th International Electrical Symposium. In this section, we have 4 presentations, and I would be happy if a presentation is about 20 minutes. Let's go. If any question, please, participants, write to chat. At the end of the presentation, I will forward them to the presenter. And let's start the presentation. First, paper presentation from Istanbul Technical University, and authors in this presentation, Kevser Ozer and Murat Yilmaz. Kevser Ozer presents. And let's start with Ozer. First of all, introduce yourself with a few minutes after presents your paper.
Hello, everyone. I am Kevser. I graduated from Istanbul Technical University, Department of Electrical Engineering. I continue my master's degree in electrical engineering, Istanbul Technical University. I will try to briefly explain our work today. We work with Associated Professor Murat Yilmaz on design and analysis of a high power density BLDC for a multi-rotor unmanned aircraft. During the presentation, I will first tell you our literature review. Then I will give information about the motor structure and material we choose when starting design. I will give requirements we have obtained for the UAV, talk about the analytical analysis result and finite element analysis result. Finally, I will talk about the power density increase work we did on the designed basic motors. Firstly, UAVs or unmanned air vehicles are aircraft that can be controlled without the need for a driver. In fact, drones are the UAVs we encounter frequently. This technology, which develops rapidly depending on battery technology, power electronic systems, and electric motor technology is now seen in many scales in our lives, drone, in defense, agriculture, cargo, etc. Air taxi, which are large-scale UAVs, were the main UAVs we worked on. As I just said, since UAVs are many scales, motor design studies have been done frequently. You can see some of them in the slide, and even in the market, many drone motors companies are designing these motors. While it is frequently encountered for small-scale drones motor design, because it is limited in the number for the new air taxi motor designs. The main reason for this is that the UAV, large-scale UAV, is used to transport people or cargo or medicine, and has a high load capacity as well as its own load. This is exactly why the empty weight of the vehicles becomes critically important. Therefore, as much power as possible from the unit weight is required for each UAV component. You can also see the components of a UAV on this picture. It simply consists of a battery, power supply, providing power, a driver circuit, and electrical motor. The motor is directly coupled to the propeller, and together they provide the thrust. The power density of these components and their efficiency are very important. This APS or electrical propulsion system are perfect more than internal combustion systems because of less noisy, cleaner than other systems. BLDC are more preferred is many significant application, brushed DC or asynchronous machine because of power density and efficiency. This system has generally outer rotor BLDC. Due to its height interior, ability to work in application with high torque chains, at the same time connect the rotor directly to the propeller because of application suitable. Another things that needs to be determined at the beginnings is the material selection, and the needs were evaluated while choosing this material. Although it has many active and passive components on motor, rotor, stator isolation, winding wire, etc. Among this magnet material for the rotor and sheet material for the stator are the materials that determine the efficiency and power density. For example, when choosing the magnet in the rotor, a magnet with a high energy multiplier and not demagnetizated at low temperature should be selected. We preferred a magnet from the neodymium iron ore magnets, which has a high power multiplier according to another magnets like ferrite. Since we do not want these magnets to be demagnetizated at low temperature, we choose a special series from the UH series. Another critical material is a sheet material for the stator. When we choosing it, we look can it provide the greatest magnetic flux density with least magnetic field strength, and the material loss is as low as possible, less loss. We choose the sheet material whose properties as given table. its material Vakodur material. Then we preferred after determining the materials in this direction, we need to determine the power and torque needs. And we looked the air tax studies in the market among various topologies. We took the vehicles of the Ehan company as reference, which carries a one person with 8 rotors and has full weight of 360 kilograms. Then we calculate the total thrust with the formula you see. The 1.5 coefficient here is a safety factor. We proceed to find the need requirements, what power, torque for a single blade plus combination for the vehicles. This mean tank motor with a nominal values of approximately 10.5 kilowatt, 75 Newton meter, and 1,300 RPM. In this way, we have actually finalized our requirements and basic decisions and start the analytical analysis part of our motor design. We follow the basic motor design process and started from the main dimension equation. After finding the basic length diameter of motor, we determined the air gap, winding determination, calculation of the dimension of slot, calculation of the fluxes, dimension of magnets. I can say that the flow while making this decision. Then we preferred the ANFIS interface for analysis. The first of these analyses was our analytical analysis over RMX board. In this part, we used the dimension that we determined for the from the basic equation, of course, by optimizing on the RMX board model. We run our model at constant power with 48 volt, and the outputs were as in this table. The motor efficiency around 93%, and get the torque we need. I have given the current density in particular because we know that in motor design, the current density affects the performance of the motor quietly. If we can't do a very good cooling, we should not exceed 6 ampere per millimeter squares, because we can damage to motor thermally. However, we know that the upper limits of current densities have been increased because of aviation application. In this system, the propeller pulls the motor with its natural flow. So we did this for a better motoring design and increased to 12 ampere per millimeter squares. Density motor, not a system that's work with linear equation. We performed our electromagnetic analysis using again ANFIS Maxwell 2D, which makes the finite element method. Here we check our flux densities, distribution of our flux lines, and torque graph parameters. For example, as you can see, our flux density is approximately 2 or 2.5 Tesla in the flux density range given for the material. Again, the flux line follow the path we want, except for minor deviation. Our moment is still sufficient for our needs. Of course, all these systems works at our nominal speed of 300 RPM in our model. Finally, our work was to examine the studies that can be done to increase the power density of the motor and apply it to basic motor. It's possible to do many studies for this, and many different studies can be seen in the literature. These may be reducing the air gap of the motor, directing the magnet, for example, Holbeck structure, increasing the moment or electrical loading. In this study, we increased the electrical load of the motor because, as I mentioned in the analytical analysis section, going up to high power densities is very useful way for this application, aviation application. Therefore, we increased the electrical load of the motor to 25 ampere per millimeter squares. And while doing this, our basic requirements were essentially the same. Changing the inner diameter of the motor and the dimension of the slot while our basic dimension. The same as the rotor diameter and the leg winding properties, the same. When the developed model in run with Maxwell 2D again, we can meet your 75 Newton meter value. We can reach the speed we want. We don't want saturation the motor. This actually reduced the weight of the motor for while doing this. The same power with a lighter motor and increase our power density. Of course, while doing this, our efficiency decreases because increased current connect to the increased copper losses. A good optimization is also important in this part. In this design, we managed to increase the power density up to 3.8 kilowatt per kilogram by keeping the efficiency at 91%. Finally, it's necessary to evaluate all the results for the design motor. In first column, we see the result of our basic design, while our second, third, four columns belong to unchanged model. As expected, the result, our analytical analysis calculation, RM export and Maxwell model for developed model are quite close to each other. Here are the columns 1 and 4 with which we must compare. Both design require values for the UAV. However, this design in which we have increased the electrical loading has made the motor lighter. However, while doing this, the efficiency decreases slightly. When these results are evaluated in the literature, these power densities, which are around 2 kilowatt per kilogram, have been increased by electrical loading and reach up to 4 kilowatt per kilogram. When we look at the efficiency, while 85% efficiency are common for small scale motor design, this efficiency go up to 95% as the motor design and scale increase large UAV. And these designs in the good place with 91 and 93% in this efficiency range. Thank you for listening.
Sir, I cannot hear you.
Thank you. Thank you. Thank you very much for your presentation, Ms. Ozer. And thank you again, Murat Yilmaz. In chat, I look no question, but I have a big question. In your study, Ms. Ozer, BLDC motor, torque, speed, and efficiency parameter very high. Other these motors. What do you think at your study, at your paper, contribution, practical application?
We selected in high technology material
Yes.
and high power density, but in market, unfortunately, these materials don't quickly find because only a specific application we use, but market motor is not good.
Okay. Your presentation is very good, and your paper is beautiful. Thank you again.
Thank you.
And our dear, we are together in second paper from Istanbul Tech University. Authors in this presentation, Ipek Kuvvetli, Alper and Lale Ergene. Topic title: PI-based ANFIS controller design for PMSM drives. Presenter, Ipek Kuvvetli. Okay.
First,
introduce yourself after share your paper and continue.
Okay, thank you for having me. Let me introduce myself first, but I'm gonna share my PowerPoint presentation here.
Yes.
And also, pointer. Yes, let me introduce myself first. I am Ipek Kuvvetli, graduated from Istanbul Technical University. And also, I'm a master's student at Istanbul Technical University in Department of Electrical Engineering. I have been working at Turkish aerospace industries for almost 5 years. I mainly focused on controlling and modeling electrical system architecture. And that's all. Today, I would like to talk about PI-based ANFIS controller design for PMSM drives. At the beginnings of the presentation, I will give a brief information as an introduction, and I will explain mathematical model of PMSM. And also I will explain speed control via field-oriented control divided into 2 groups, conventional PI control and ANFIS control. And also I'm going to show you some simulation results and comparisons, and I will conclude at the end. In the introduction, 3-phase motors, permanent magnet synchronous motors are 3-phase motors. Their windings are distributed 120 degrees phase apart. They are very popular because of higher power density, higher efficiency, improved torque to inertia ratio, and reduced torque ripples with advanced control techniques. And also, they are widely utilized in aerial and electric vehicles, military applications, robotics, and energy sector, as you know. I would like to share with you the motor, PMSM motor that we used. It's technique 2310P. And also I would like to talk about mathematical model of PMSM. The simplified voltage expressions for the PMSM in the direct and quadrature axis are given here. And these expressions are related to stator resistance, stator inductance, rotor speed, and permanent magnetic flux. And the developed electromagnetic torque expressions and rotor mechanical dynamics for the surface-mounted PMSM are integrated with pole pair, load torque, damping, and inertia. And you can see the expressions. In surface-mounted PMSM, direct axis inductance is equal to quadrature axis inductance. So these formulas are simplified according to the type of surface-mounted PMSM. And also, I would like to share with you motor specification of Technique 2310P. You can see the parameters, pole pair, permanent magnetic flux, inertia, rated torque, base speed, rated current, and maximum speed. And also you can see the units and their values. Our motor, as we talked before, is a low voltage 3-phase synchronous permanent magnetic servo motor. It has built-in an encoder, and also it has a sinusoidal back EMF. Our control system is Texas Instruments TMS320F2837XD. Inverter model is Texas Instruments DRV8305, and the switching frequency is 40 kilohertz. And DC link voltage is 24 volts, you see here. In order to create PMSM derived model in MATLAB environments, we have to select all sampling time appropriately. So I'm going to show you the sampling time of each component. The sampling time of the motor is 25 microseconds, and the same sampling time of the inverter is same as the sampling time of the motor. And the sampling time of the current controller is 50 microseconds, and the sampling time of the speed controller is 500 microseconds. As you notice that the sampling time of the speed controller is higher than the other components because the speed controller is placed on outer loop, and that's why its frequency is lower than the other components. I will continue with speed control via field-oriented control with PI control. Sorry. First of all, I'm going to show you the field-oriented diagram here. And also, I will explain the purpose of field-oriented control. The field-oriented control, the purpose of field-oriented control is to control the torque and flux using appropriate field orientations by controlling phase currents in the stator. And as you see here, the field-oriented control method incorporates with Park and Clark transforms. I would like to explain each transform. First of all, I will begin with Clark transform. In Clark transform, three-phase quantities in three-phase reference frame are converted into two-axis quantities in orthogonal stationary reference frame. In Park transform, as you see here, two-axis quantities in orthogonal stationary reference frame are transformed into two-axis quantities in rotating reference frame. How to find PID parameters with field-oriented control? I have used PID tuner app in MATLAB to find parameters of PI controller. Our design criteria overshoots should be less than 20% at no load condition, and the setting time should be less than 0.15 seconds. And also, I have given the PI parameters in a table here. I will continue with speed control with ANFIS controller But before ANFIS controller design in MATLAB in Simulink, I will explain ANFIS mechanisms. So ANFIS means Adaptive Neurophasy Inference System using Takagi-Sugeno fuzzy models, and it's the combination of fuzzy inference system and the neural networks. You see the ANFIS architecture that is simplified according to two inputs, X and Y are taken. You see here, I will explain all layers step by step. At the first layer, you see the labels and the membership functions. And these membership function parameters are adjusted by backpropagation algorithm. And these layers, these nodes are not fixed. These layers are adaptive. At layer 2, you see AND operators called T-norm operators. And these nodes are fixed. At layer 3, you see the normalizer. So these nodes you see here are fixed nodes. The formula utilized to find normalized firing strength is given here. And also layer 4 is adaptive. As you see, the function of F1 and F2 are adjusted by backpropagation algorithm. These functions are outputs of the Takagi-Sugeno fuzzy models. Consequent parameters are adjusted, and you can see the formula, see the expressions. And at layer 5, the weighted average depacification is calculated. Also, you see the formula related to weighted average depacification. I would like to continue with ANFIS controller design in MATLAB Simulink environment. I gave ANFIS controller model in PMSM here, and you see scaling factors. These scaling factors offer improved performance and stability, enhanced characteristic of controller. We have two inputs, as one of them is error, you see here, and one of them is the change in error. The error is difference between actual motor speed and the reference speed. And the change in error, as you know, the change in the error sign, this branch. And I would like to talk about how to train ANFIS data in order to minimize the error between actual data and data collected dynamic model with PI controller. Speed reference inputs should cover the entire range. So all speeds range is divided into 20 sections as 10 positive and 10 negative values. And also, I'm going to show you the membership function of ANFIS controller that I designed. I will share ANFIS toolbox interface with you. The error, these blocks represents the membership function of error, and these blocks represents the membership function of change in error. After many testing, after many trial, the most effective adaptive speed performance for the design is obtained as Sugeno type 5 triangular membership functions for each input. And also, as you know, we have function outputs, we have told before. And I would like to share with you the surface viewer of ANFIS. And this picture, this image provides the estimation and controlling the output signal of the controller. I will continue with results and comparisons. These results are only about the simulation results. We have 3 scenarios. At the first one, the motor operates at constant speed under no load. And we can investigate direct and quadrature X voltage and current and torque and speed characteristics versus time. And as you see here, ANFIS offers reduced overshoot and short setting time. And also I will talk about the second scenario. At the second scenario, the motor operates at constant speed with loading. As you see here, you can consider all the characteristics. ANFIS provides reduced overshoot, short settling time, and of course, more robust control with loading under 0.20 Newton meter. And also, I will examine speed reversal characteristics with PMSM drive. As you consider 0.5 second characteristic here, and you see damped response, and therefore ANFIS offers a critically damped response within the short setting time. And also, I'm going to show you PI and ANFIS performance results in terms of overshoots, setting time, and steady state error. There is a drawback of ANFIS, as you see here. The steady state error of ANFIS controller is 0.13%. This is so minimal, so this can be ignored, this can be rounded to 0. And it's not the problem, I think. And in conclusion section, the proposed ANFIS system needs the extraction of the training data from a PMSM dynamic model with a conventional PI controller to improve motor performance. And ANFIS methods shows a better performance to overshoot in speed. And also, ANFIS design has minimized settling time compared to the PI controller. And I talked about the disadvantage of ANFIS controller, and the part of training data in ANFIS requires more time, and the selection of the number and type of memory functions affects the training error deeply. And thank you for listening.
Thank you, Ms. Ipek. Any question, answer part?
Okay.
I look again, chat. There is no any question, but I ask you a bit question.
Okay.
What is your opinion, advantage proposed ANFIS system according to the conventional PID control?
ANFIS controller offers short setting time.
Briefly, you describe at your paper.
Yeah.
For example, speed, about torque, about efficiency or loss. Did you understand?
Yeah, I understood you, but actually, I show all characteristics, all disadvantage and advantage. So, in my opinion, I prefer ANFIS controller because considering the performance results in terms of overshoots and the settling time. But I cannot say the ANFIS controller is the best controller type. I cannot say this.
Thank you very much.
Okay.
Ms. Kuvvetli, your English language was good, presentation was beautiful, and good luck from new paper. Okay.
Thank you. Have a nice day.
Ladies and gentlemen, we are in third paper. Third paper is coming from, again, Istanbul Technical University. Topic title, third paper, Effects of Voltage Harmonics on the No-Load Losses of Three-Phase Distribution Transformer. Authors in this presentation, Kamran, Dawood, and Guven, Komurgoz. Presenter, Kamran, Dawood. I see you, Mr. Dawood, and please introduce yourself and after continue.
Good morning, everyone. I'm Kamran Dawood, and I'm here to present my paper. The topic of the paper is effect of voltage harmonics on the no-load losses of the three-phase distribution transformer. I'm currently pursuing a PhD in the Istanbul Technical University, and as you told that my co-author is Guven Komurgoz. So let's start the presentation. My presentation will be divided into 5 sections, and I will try to keep it as simple as possible. So first, I will introduce about the transformers and some losses, then what we have done in our work. Then we will see the design parameters of the transformer, that what was the voltage levels of the transformer and what material we use for the core as well. In the third section, I will tell some theoretical knowledge of the losses in the power transformer. Then we look about the uses of the finite element method in electrical machines or any field of the engineering. And in the last, we will discuss and conclude the simulation work, and we will simulate about how the harmonics and other important parameters affect the no-load losses of the transformer. As we know that transformer is very important part of the distribution and transmission system. In the distribution system, the transformer is one of the major components. When we talk about the transformer, the normal age of the transformer is more than 40 years. Generally, I can't say more than, but it is normally 40 years. And the operating cost due to the no-load losses or core losses is the initial or making exceed the total cost of the transformer. So we must have to take care about the no-load losses. So in some cases, transformer didn't work, but no-load is always there. And almost 25% of the distribution and total transmission losses in the electrical system or in the electrical grids are due to the no-load losses of the transformer. And we all know that in last few decades, the use of the direct current components and other power electronic equipments are increasing significantly, and they are making harmonics in the power system. So as we know that non-sinusoidal voltage sources lead to the higher losses and decreases the life of the transformer, because higher losses means higher temperature of the transformer. So in study, what we have done that we make the 3-dimensional model of the transformer to evaluate the 4 different conditions for the no-load losses. These are the 4 conditions which are given below. So what we have done that in the first condition, we did the no-load losses without any harmonics. We also did the experimental work on that. In the second condition, we have added 15% of the third harmonics. In the third condition, we have added the 30% of the third harmonics. And in the last condition, we have added the 30% of the 5 harmonics. As we know that how harmonics affect the no-load losses, that with the increase in the number of the percentage of the harmonics, no-load will be also increases. But we don't know that how much it is and how the third and fifth harmonic different to each other if we are making the same percentage. So these are some of the parameters of the transformer. So in this study, we have used 3-phase distribution transformer with a voltage level of 1.25 megawatt ampere and a voltage level of 34.5 means 34,500 watt and 400 watt was investigated. In the core, we have used M5 CRGO steel material. So we can use any other, but in our experimental work, we have used M5 CRGO material, and other parameter of important parameter of the transformer are given here, like high voltage was, as I told, 34,500, low voltage side watt 400 watt. So we can see other parameters as well. So we all know that the losses in the transformer can be stated as the difference between the power of the input and output. So what power we are giving to the transformer and what we are taking out is the difference between the power of input and output. And losses in the transformer can be divided into, these are two major losses. So we have other as well, like stray losses, or like other losses are there as well. But the major losses of the transformer are load losses and no load losses. Load losses, everyone know that the load losses is also known as copper losses. The main thing is that these are mainly due to the copper or aluminum or any other conductor we are using in the transformer as a winding. These are also known as the ohmic losses or ohmic resistance, which are mainly due to the ohmic resistance of the conductor which is being used in the winding of the transformer. So these are some of the formula that in the primary winding it can be is a product of the current and resistance of the transformer. Similarly, in the secondary winding as well, so it is the square of the current multiplied by the resistance of any conductor. When we talk about the no load losses, these are also known as iron losses, or sometimes we can call it as a core losses as well. These losses can be divided into two parts: dielectric current losses and high stress losses. And current loss, easy current losses and high stress losses. We have another third one, dielectric losses, but the ratio of this is just only 1%. So, and these all of the losses mainly depend on the magnetic property of the core material and the lamination of the core as well, and the structure of the core used for the construction of the core. So, as I told that the main part of the no load losses are easy current and high stress losses, which contribute almost 99% of the iron losses. These are some of the formula to find the high stress losses and easy current losses. As I told that the major part of the no load losses is due to the high stress losses and easy current losses. We can also see that it is written that half of the no load losses are mainly due to the high stress losses, and this depends on the frequency of magnetic reversals, flux density, volume, and grade of the core materials. So we can find the higher stress losses with the equation 1. Similarly, for the easy current, we know that easy current also depend on the lamination of the transformer. The smaller the lamination, the lower the easy current losses will be. So we can decrease the easy current losses by decreasing the space of the lamination, or like the size of the lamination. So minimum the size, less the losses will be, as I told that. So solid cores will be more easy current losses. Equation 2 or 3 can be used to find the easy current losses and overall no load losses. Another formula to find the no load losses is that we can multiply the core loss per kilogram with the total weight of the core in kilograms. Generally what happens that any manufacturer of the core or manufacturer material of the core, like M5, M4, they give you the particular value of the losses per kilogram. So we, like for the M5, it is 1 kilowatt per 1.7 Tesla. So it will be given by the manufacturer company of the core material. So what happened that we know about that how we can find the core losses, but there are in the previous study there's no work about the harmonics, how the different harmonics affect the no load losses. So we will see how the different amplitude, like that, how 15% or 20% or 30% affect the no load losses, how the order, like third or fifth order, affect the no load losses. So as I told that this is a very general knowledge that these are computational technique, or finite element method is one of the good technique to solve the engineering problems, as we know that we cannot solve every geometry by the analytical method, and we cannot define every material in the analytical method. So we have just two techniques, like just practical or prototypes, or we have to do any analytical work. And these techniques are being used in every field, like some of in our field examples are thermal analysis, electromagnetic analysis, transient analysis, and mechanical analysis. Okay, so let's talk about some results as well. So what we have done in the first condition, as I told you, that during the normal condition, we didn't add any no load, any harmonics in our simulation. So these are the results of magnetic flux density. The original magnetic flux density was 1.6 something. So we have find a suitable result as well for the simulation. We keep the number of meshes higher. So the accuracy of the model will be higher as well. It took some time, like for a single simulation, it takes more than 7 days. So for 4 or 5 simulation, it takes more than 1 month. So the work is very long as we see the duration of the simulation. Let's see the results of the simulation. Without any harmonic, we find that the overall losses of the transformer with 1850 watt. So we can see that different highest losses and ED current losses as well. As I told that the highest losses are more than 50%, we can say that here it is like 63 to 64% without any harmonics. These are the results as experimental and numerical and analytical. As I told that analytical we can found with the formula, with the last formula. So the company gave us that with the 1.62 the voltage or loss was like 890 watt per kg. So we found it by that analytical method. And we can see that the difference between the experimental and numerical method was just 4.46%. In the international standard, they allow like 10%. It can be plus or minus 10%. So these results are suitable, and we can go forward for the harmonics as well. And we can see from the result that the difference between the analytical and experimental result was like 4.74%. And the difference between the finite element method and analytical method was less than 1%. So we can continue with the other work as well. So we can add the harmonics in the voltage to see the how harmonic affect the overall core losses. As I told that the most part of the no load losses was generally from the highest losses. It is 63.41%, and for the ED current losses, it is 36.6%. So what we have done that after confirming the accuracy of the three-dimensional finite element method, we have analyzed more three conditions that is given in this table. In the first, second condition, we have added 15% of the third harmonic. In the third condition, we have added the 30% of the third harmonic. In the fourth condition, we have added 30% of the fifth harmonic. I said that we have added the harmonic voltages in the premier voltage to see the no load losses of the transformer. And the main aim of this study is to analyze the effect of the different harmonic orders, as I told previously, and magnitude on the no load losses. These are the results. As we can see that the no load losses during the first condition was 1.84 like that. In this type, we have increased to 1.86. And we have seen another thing that with the increase in the 15% of third harmonic, the voltage or no load losses increased to just 0.16%. But the another thing is that it is just increase in the ED current losses. So ED current losses are more increasing in the higher harmonics. So in the third condition, we did, as I told you, that in the third condition, we have added 30% of the third harmonic, and the no load losses increased to the 1.9%. As I told that, you can see that highest losses are almost same, but they're affecting more on the ED current losses. So that means there is something in the lamination or like that. Similarly, for the fourth condition, we can see that in the fourth condition, what we have done that we increased the fifth harmonic just by 30%. In the previous case, we saw that the no load losses was just 1.88 kilowatt, but with the same percentage of the harmonic, but we just different the fifth harmonic with the third one, it increased to the more level, like that third harmonic, effect of the third harmonic and fifth harmonic is not same. The results show like that. So let's conclude it that we saw that in the last condition, the difference between the experimental and the finite element method was 12.15. So we, as I told you that if we increase with the more than 10%, or like if the difference between the finite element method and experimental method is more than 10%, it is not acceptable in the international standards. So this work is actually about how harmonics affect the overall no load losses. In the results, I can conclude that the harmonics affect more in the eddy current losses. So during the first condition, the share of the eddy current was just 36.6%. In the other condition, you can saw that it increased almost to the 38%. Like in the third condition, it was till 38.8%. So let's conclude our work. In this work, we have used 1250 kilowatt ampere three-phase transformer under sinusoidal and non-sinusoidal voltage sources. The finite elements analysis or our results show that higher order generate the higher no load losses, like as compared to the third one, fifth make the more no load losses. And we can come another result that as higher losses generally depend the higher hotspot temperature in the transformer, as I told previously, due to which these harmonics do not only affect the no load losses, but the overall life of the transformer can also be decreased. So we can also come to the another comparison that harmonics can also do not fulfill the international standard tolerance, like they just allow for maximum 10%. So in the fourth condition, the difference was more than like 10%, it was 12%. Thank you for your listening. If you have any question, I am here to answer you.
Thank you, Mr. Dawood. Where are you from?
I'm from Pakistan, sir.
Pardon?
Pakistan.
Pakistan. Okay. You are speaking very fast. Harmonics, every time problem in electrical, if production, distribution, or consumption. In your study, any effects, current harmonics, you think only effects of voltage?
No, we have added the harmonics on the primary voltage, and we saw that it affects the more easy current. It affects the more easy current as compared to the highest losses. So we come to the conclusion that maybe there's a problem with the lamination or like that. In the real work, we can, if it is accepted in the extended version, we will do a practical work, whether these results are real or not, whether these results are acceptable as compared to the experimental or not.
Yes, yes. Thank you for your answer. Thank you again, Mr. Dawood and Mr. Komurgoz. Best you from new papers.
Thank you, sir.
Okay. We are together with last paper. Last paper is from Gazi University from Ankara. And topic title in this paper, analysis of short circuit electromagnetic force in a three-winding transformer used in solar system. And others in this presentation, Amir, Jahi, and Ires Iskender. I think Amir is ready. Okay, Amir, first introduce yourself and after at you.
Okay. Hello all. Thank you, Professor Ozdemir.
Thank you.
Before I start my presentation, let me briefly introduce myself. My name is Amir, and I received my master's degree in electrical and electronics engineering from Gazi University. Now, currently, I am a PhD student at the same university, and at the same time, I'm working as a electrical design team leader at SAM Transformator company. As you say, my paper is about analysis of short-circuit electromagnetic force in a three-winding transformer used in solar system.
Sorry, Amir.
Yeah. Yes.
Full paper.
Yes. Can you see the full?
Yes, I see it.
Okay,
Continue.
continue. My presentation is consist of the 6 part. In the first part, is about the introduction. The second part is a brief review of the transformer design, and the next part is about the electromagnetic field analysis. The second part, the next part is about my transformer model, and after that a simulation study, and the last part is about the conclusion of our work, our study. Let me move to the introduction. Power transmission from solar systems to grid is achieved using step-up transformers. Generally, this type of the transformer is energized from 2 inverter with or without variable frequency. Power transformers deals with a variety of mechanical, electrical, and thermal stresses during normal lifetime operation. Transient electromagnetic forces cause mechanical stress on transformer parameters, where accurate calculation of these forces with traditional methods is extremely hard due to the complex geometry of the transformer. Accordingly, in this study, the electromagnetic forces takes place in the winding of a photovoltaic transformer are investigated, and for calculation of these forces, the 3D and 2D model of transformer is adapted in ANFIS workbench. The analysis of electromagnetic forces during the 3-line fault on high voltage side of the transformer are performed by the finite element method and compared with the analytical results. The numerical modeling technique discussed in this study would be useful in the design stage of a PV transformer with regard to evaluate ability of transformer to withstand the short circuit current. Here, I would like to brief review of the transformer design. The design of the conventional transformer begins with the design of active part of the transformer, which consists of the core section, magnetic flux density, high voltage and low voltage turn number, and the current density of the conductor. Afterwards, the design of the transformer tank and cooling valves is done. In the electromechanical field analysis, the transient currents flowing into windings are important parameter in the calculation of the electromagnetic force. When a short circuit, yes,
Amir,
yes,
your slide doesn't flow. We see first slide.
Oh, I try to share again.
Okay, share again.
Share again the presentation.
Again, first slow.
Yes. Can you see now?
We see, no problem. But only
the first page.
Yes, first slide. But other we don't see.
Okay.
Only first slide in screen.
Sorry for that. I try to share my full screen, and I think the problem.
Okay. Continue.
Yes.
Okay.
Okay.
Continue.
Here in the
no problem.
yes. Now we are. I was talking about the electromechanical field analysis. As I said, the transient currents flowing into windings are important parameter in the calculation of the electromagnetic forces. When a short circuit condition occurs, the high magnitude currents, which is several times greater than the rated current of the transformer, flows into the winding. These transient currents can be approximately expressed as follows. In this equation, the R, X, and L is resistance, resistance, reactance, and inductance respectively. The electromagnetic forces are calculated from the local magnetic flux density in the transformer. When current flows into the windings of the transformer, the governing equation of the magnetic field is as follows, where in this equation A represent the magnetic potential, magnetic vector potential, and J represent the current density of the transformer. The force on the transformer is expressed by the Lorentz force is given in terms of the current density in the volume as follows, where also the B is represent the magnetic field density in this equation. Two different forces occurs in the transformer. The first of these is radial forces, which can be calculated as the below formula. The radial component of the electromagnetic force destroys the insulating material between the core and winding, or between the winding layers. The other force occurring is axial force, which can be calculated as a below equation. The axial force at the upper and the bottom of the winding acts as a tensile or compressive force in the axial direction and may cause the winding structure to bend. Here, I would like to talk about our transformer model. In our study, a 5.1 MVA, 34.5 kilovolt to 0.66 kilovolt, 3 concentric winding transformer with two 2.55 MVA low voltage winding modeled and implemented. The transformer is fed through 2 separate inverters, and as you can see in the figure, the winding configuration of the considered transformer is shown with 1 high voltage winding in a green color interleaved between 2 low voltage winding. The brief design specification of the considered transformer are shown in the table. The transformer secondary or high voltage rated current is 65.3. The primary rated current is 2213, and the vector group of the transformer is DYN11, YN11. It means we have 2 low voltage winding in our transformer with a Y or star connection. The primary turn numbers of the transformer is 13. The primary conductor of the transformer is aluminum foil. The secondary term numbers of the transformer is 1177, and the aluminum rectangular paper used for the secondary conductor. The maximum flux density of the core in our transformer is about 1.65 Tesla. The short circuit impedance of the full power, I mean 5.1 MVA, is 6%. The short circuit impedance of the high voltage winding and inner low voltage winding is about 6.4%, and the short circuit impedance of the high voltage and outer LV winding is about 7.2% in our model and our transformer. At the simulation study, during the short circuit fault, transformers may be damaged by the transient current, which is several times greater than the normal operation condition. For the electromagnetic analysis, a post-set 3-line HV winding short circuit condition as per IEC 60076-5 was applied to subject transformer with three-phase source applying to the LV winding, low voltage winding, and the high voltage winding short circuited condition. The post-set short circuit condition of simulation is shown in figure. As you can see, the left side is our transformer high voltage circuit, and the right side is two circuit, which means the two low voltage winding of the transformer. The short circuit is we apply the short circuit from the high voltage side of the transformer, and according to the simulation result, the low voltage, the voltage and current of the high voltage and primary side of the transformer is shown here. In the upper figure in the screen, you can see the three-phase short circuit line current of the high voltage winding, which is about 1.2 kiloampere. In the lower figure, you can see the three-phase voltage of the low voltage winding of the transformer, which is about 381 volt. In this page, you can see the three-phase short circuit current of the low voltage winding, inner low voltage winding, which it's calculated about 36 kiloampere. And at the bottom figure, you can see the three-phase short circuit current relative to the outer low voltage winding, which is calculated about 30 kiloampere. In this page, the radial force vector distribution in the middle winding obtained from the 3D and 2D model is shown. As you can see at the left picture or left figure, you can see the radial force in the inner LV winding of the transformer. At the right picture, you can see the radial forces in the high voltage winding of the transformer, and at the bottom figure you can see the radial force at the outer low voltage winding of the transformer during the short circuit condition. And it is seen that the radial force in the LV in the outer LV winding has direction to the tungsten side, and the radial force in the LV inner LV winding is opposite, have direction opposite to the LV outer LV, and its direction is to core side. And the high voltage winding has direction of radial force to the both side, but its magnitude is higher in to the tank side, and also the radial forces has greater value in the middle area of the windings, because in these areas the axial flux is higher. In this page, the top view of the 3D model of the transformer is shown. As I explained, the result of the radial force is same. As you can see, the inner LV winding has direction to the core side, and the outer LV winding is has direction to the tank side, and the HV winding, as you can see in the middle figure or picture. It has a direction to the both side, but its magnitude to the outside or tank side is higher than the inner side. Figure below shows the simulation result of radial electromagnetic forces under short circuit condition along the windings of the transformer. And according to the simulation result, the high voltage radial forces in the high voltage winding is calculated about 1,248 kilonewton, where its value is 480 in lower in inner LV winding and 657 in outer LV winding. The total deformation and stress at outer LV winding of the middle phase due to the electromagnetic forces during the short circuit faults is given in figure. It's clear from the figure that the electromagnetic force in the middle of the windings is relatively high compared to the two ends of the winding due to the higher axial leakage in the middle of the winding under short circuit condition with a maximum value of 70 to 82 kilopascal. In this table, the comparison of the radial electromagnetic forces and short circuit current between the simulation and calculation result is given. According to the results, the short circuit current in the inner LV winding is about 34 kiloampere, where it is 36 kiloampere extracted from the simulation result, and the difference between the analytical and simulation or a numerical result is about 3% for the inner low voltage winding. It's at the high voltage winding, the short circuit current is calculated about 0.7 kiloampere, and the simulation results shows the values about 0.7 kiloampere, and the deviation between the simulation and analytical is less than 5%, or it is about 3%. For the low voltage winding, the short circuit current is calculated about 30 kiloampere, and it's calculated from the simulation result about 31 kiloampere, and the difference or deviation between these values is about 1%. And also for the radial forces, the calculation result for the inner LV winding is 425, and it's 480 from simulation result, and the values, the radial force in the high voltage winding according to the calculation result is about 1,403, and it's calculated about 1,000. It's calculated about 1248 from the simulation result. For the low voltage winding, for the outer low voltage winding, the radial forces calculated from the analytical method is about 591, and it's 657 from the simulation result. In the conclusion, in our paper, the FAM has been used to predict the transient electromagnetic forces imposed on the PV transformer. The short circuit forces must be considered as one of the main factors during the design of the transformer. Due to the higher forces during the short circuit current, transformer can be damaged with these forces, and these forces can affect the working of the transformer. A three-phase short circuit condition applied to the subjected transformer terminal has been addressed in this paper. A 3D and 2D transformer model has been considered to calculate the transient electromagnetic forces. The transient current due to the short circuit fault in PV transformer was computed and the results are in good agreement with the traditional analytical calculation values. The numerical modeling technique considered in this paper to analysis of short circuit impact on the winding can help for better determining the cause of winding deformation and expected to be useful in the design stage of the photovoltaic transformers. Regarding to evaluating the ability of transformer to withstand the dynamic effects of short circuit, also might be helpful for the theoretical evaluation of the ability to withstand the dynamic effects of short circuit and can be save the expensive type test prices. Thank you for your attention. If you have any question, please let me know.
Okay, thank you, Mr. Amir. I look, no raise hand, no written question at chat, but
yeah.
I ask to you general question. How
Yes.
does this study contribute to you? For example, from here, can you go to wind system? Generally.
Mm-hmm. I think in my study, as I mean, you are asking about the results of our study. And thank you. First of all, thank you for your question. The result of our study is, as I said, is about the electromagnetic forces in the transformer. For example, from some in the big transformer, in the power transformer, the short circuit test is very expensive. Also, in Turkey, we don't have any facility or test laboratory which was performed the short circuit test for the power transformer. I mean, I think in Bustyal can apply the short circuit test up to the 2.5 MVA transformer. So in the design stage of the transformer, we have a type test for the transformer. The short circuit withstand ability is one of these type tests. So some customers ask the type test for the transformer, and we should apply or perform type test, or we can confirm the ability of the transformer to the withstand to short circuit forces with the numerical or analytical calculation. And in this study, we can use the finite, we shows and confirm the ability of the numerical calculation to help us to show the transformer ability to withstand the short circuit condition. I think I
okay, enough answer. Thank you.
Answer your question.
Thank you. And there is a question, Mr. Dawood. Dawood, you can open the sound.
Thank you for the wonderful presentation, Amir. I have one question.
Open the camera.
Okay.
Open the camera. And all of presenter, can you open the camera?
Amir, thank you for your wonderful presentation.
And
I have one
Kevser,
question.
okay.
Actually, you said that the direction of the high voltage force was toward the tank. Can you open that slide? I have
Yes.
question.
Here.
Okay.
This is slide, I think.
Yeah, we can see
Okay,
here
come
that
on.
the distance between the high voltage and low voltage winding 2 is very small. So maybe that is the reason, instead of it is going to the tank, so it always go to the low voltage side. It is the reason. What do you think about it?
Yes, maybe you are true. Firstly, I thank you for your attention and thank you for your question, Mr. Dawood. In normal transformer or in two-winding transformer, it's like you said. Normally the direction for the LV winding is to the into the core side, and the direction of the high voltage winding is to the tank side. But as you say, maybe the distance of the winding, between the winding cause this direction, or if in the three winding transformer, maybe we have this direction.
You can do like that. Make the distance equal, then we can conclude anything. I think like that, because in generally high voltage side is different, but in your work the space is also different between the low voltage side and the second low voltage side. Maybe that is the reason. So maybe there's another work.
Yes, maybe in our study the distance is different, because we try to adjust the short circuit, as you know, the short circuit impedance in our transformer, and so the distance is different between two LV winding. Yes.
Thank you. Got it.
Thank you for your
Thank
question.
you for everyone. Especially thanks a lot, Kevser Ozer, Ipek Kuvvetli, Kamran Dawood, and Amir, Jahi, and others. And this session have finished. I hope this session was helpful for everyone. And Eleco conference goes on at full speed. Continue, follow us. See you another good platform.
Thank you. See you.
Thank you, sir.
Thank you.